Cb, and the reactants trade places to form Ad and Cb. All right, can you see that? These compounds here are ionic compounds, generally. Ionic. Meaning that they're a combination between what? A metal and a non-metal, right? So this one would probably be the what? The metal, right? What's a good ionic compound that we can use as a model? Sodium chloride, right? NaCl, right? So there's our metal and our non-metal. So metal, non-metal, right? Metal, non-metal. So the metals still end up in front, but they've just traded places. Right? This is called a metathesis reaction, or a double replacement reaction. And it allows us to understand a lot about chemistry. They're relatively typical reactions, so it's what we're going to talk about next. But before we get too far into it, we have to get some understanding about these reactions, because these reactions don't happen like this, where we have a pile of one salt and a pile of another salt. This would be our AB, this is our Cb, right? Two ionic compounds. We don't put them together in some bowl and just smush them together, right? These metathesis reactions, or double replacement reactions, occur when you have a solution of AB, all right, and a solution of Cb. You mix a little bit of both into a container, and the result is A and D find each other, and C and D find each other. Okay? So these reactions all happen in solution. So we can see that these two are going to be aqueous. Right? So to talk about these reactions, we have to have a conversation about some vocabulary necessary to describe AB and Cb in these water solutions. Right? The first word we want to kind of make sure we're comfortable with is the word solution. A solution is a mixture where you have a solvent and a solute. In this case, our solvent would be water. It's the highest concentration. Our solute is whatever we put in there to dissolve in the water. Okay? A solution is a homogeneous mixture. So if I put some compound, here I have a container full of water, let's say, and I put some compound in it and it just makes a pile at the bottom because it doesn't dissolve, that's not a solution. Right? That's a heterogeneous mixture. This isn't something that you're going to be able to perform chemistry with very effectively, right? Because you don't know if any of your stuff actually dissolved in the water. If you were to combine two salts like this together, you won't get a very effective interaction of the compounds. So a lot of chemistry occurs in solutions or in aqueous conditions. Okay? So solvent, solute, solution, concentration, right? That's talking about how much of your solute you have in a given solution. Some other terms, dilute, not a lot, right? Probably not a new word for you. Concentrated, a lot of solute. In fact, that can mean if it's concentrated, you can't put any more solute in. Now, you guys have some experience making solutions in your life that are concentrated solutions. Have you ever eaten cereal that needed a little bit of sugar to taste good? That's not very frequently nowadays, is it? Or does somebody still use sugar? Put sugar in their cereal? Yeah? What kind of cereal needs sugar nowadays? Fruit Loops? Cornflakes. Cornflakes. Yes, cornflakes is a good example, right? Because if you don't have some sugar, it's like, it's okay. You need a little bit of sugar. So when you do that, you put a little bit of sugar in, right? And you're done with the cornflakes. What do you have at the bottom? Yeah, there's a little pile of sugar there, right? So that's an example of a solution. What would be the solvent in that solution? Solvent, the thing that's in the highest concentration. Milk, and which is water, right? the solute in that solution would be what? Yeah, the sugar. You put the sugar in there and you're hoping it would all dissolve, and it does do a fine job, but in the end, it's way too concentrated, right? So it doesn't all dissolve. Okay, so we have these other terms. Saturated. Saturated is another term or another way to talk about how much solute we have dissolved in the solution. If it's saturated, this slideshow here has one of those. If it's saturated, that's kind of like the same as concentrated. You can't add any more. Solute. Solubility. We can actually quantify how much solute can be dissolved. Right? We can quantify that. So there is some mass of solute that we put into a given mass of solvent. You guys need some slides? Yeah. Anybody else need slides? Oh, back there. Okay. Unsaturated means that we can still add more solute. Supersaturated, you can get a situation where you have more solute dissolved than the solvent can theoretically contain. Has anybody ever made homemade syrup before? Yeah? Generally, the recipes for homemade syrup are like a ton of sugar, a little bit of water, and then what do? You heat it. You get it hot. Because when things get hot, they can dissolve more of the solute. So the water, if it's hot, can dissolve more of the solute. Then when you're done, you eat some of the syrup, but you don't finish it all. You put it into the fridge, and it will crystallize out. Right? The salt, the sugar will come out, unless you've added something else like some corn syrup or honey or something to help stabilize that solution. Right? So here's an example of a saturated solution. This solution here is water with a salt in it. However, more salt was added than could be dissolved. It was heated and then slowly cooled. So it's super saturated. And then if we just kind of disturb it gently, we'll see it precipitate out. Drop a little tiny drop of something in there, and you'll see it. Did you see it? It went really fast. Let's try it. There it is. And then we see the crystals in there precipitate out. Right? All the salt that was in there got disturbed, and it found each other, and then they just solidified. And now this whole thing is like one solid piece. It's saturated with water. It has lots of water, but if you turn it upside down, it won't pour out. Right? It's stuck there. Right? So that's an example of a supersaturated solution, and this is kind of a still frame of what happens. Crystals work their way out, work themselves out, and precipitate. So that's called a precipitate. Precipitate, when a solid comes out of a solution. So here's a question about solubility. If you know the solubility of a solution of sodium chloride is 39 grams for every 100 grams of water at 100 degrees Celsius, we want to know what the solution would be if we put 10 grams into 50 grams of water at that temperature. Alright? So with the solution, 10 grams into 50 grams of water, would it be saturated, unsaturated, supersaturated? None of them. What do you think? How much should dissolve in 50 grams of water? You know how much dissolves in 100 grams of water? Can you find out how much would dissolve in 50 grams of water? About half that much, is that right? So, what does that mean? Is the solution going to be saturated, unsaturated? Saturated? Super saturated? How much should be able to dissolve in 50 grams of water? 39 and 100, about half of that, a little less than 20 in the 50. But we're only putting 10 in. So what does that mean? It's unsaturated. Unsaturated. Right? There's a lot more solute that could dissolve, up to 19 and a half and stuff. Right? Any questions on this? Yes. Question? Didn't quite get it? Okay. So, we were told that the solubility, which means how much of that salt, could dissolve in the water at a, they're going to have to give you some information about the temperature generally because solubility is temperature dependent. Right? They're saying, here's a container, here's 100 mils of water. If I put salt in here and stir it around, it'll dissolve, but as soon as I get over 39 grams, it'll start making a pile on the bottom. So then we say our solution is saturated, because any extra salt we put in, it just contributes to the pile, not more becomes dissolved. Right? And they said that you can put in 39 grams of salt for every 100 milliliters of water. Now, the density of water is 1, so you could say 100 grams of water is the same as 100 mils. So they say this is the saturation limit, right? You can't put any more. So if I have a container over here, smaller one, with only 50 mils of water, and then I put in how much salt? 10 grams of salt. Is the resulting solution going to have a pile of salt at the bottom? Is it going to be saturated? Saturated would mean you can't add any more. That's as much as you can add. No, it's going to be unsaturated. I can still add something.
So what's an example of supersaturated?
So a supersaturated solution will be one where we added 39 grams to this 50 milliliters of water, right? And they wouldn't be able to ask you the question like this. They'd have to say, this is the saturation limit, but we heated the solution hotter, dissolved more than the saturation limit, and then cooled it down. What do you call that solution that's left over? That would be a supersaturated solution. Yeah?
Was the video that we saw earlier super saturated?
That was an example of a solution that was supersaturated, and it was also an example of a scenario that gradually, if you disturb it too much, the precipitate will come out, the salt will come out. Okay, so then, what happens when we take a salt like AB and put it into water? What happens? Let's use an example like sodium chloride. NaCl, it's a solid, we take it and we put it into water. Now, this is very chemical in nature, but it's not kind of on the edge of a chemical reaction itself. Because what happens is, the sodium ions separate from the chloride ions. And now, instead of saying sodium chloride solid, you say sodium ions and chloride ions are floating around in the solution surrounded by water. And we'll show this little video of how this sort of thing happens. Okay? Salt, ionic compound, right? They reside in this kind of a structure. What did we say this kind of a structure is? A three-dimensional lattice. Do you guys remember talking about this? A three-dimensional lattice. Did you see it okay? Oops. Three-dimensional lattice is alternating ions of whatever your compound is. So in this case, we can say the big green ones are chloride ions, the white ones are sodium ions, right? So this is what salt looks like. It's actually the structure of these crystals that cause, if you look under a microscope or look really tiny salt crystals, they're going to have the same shape as this. So at an atomic level, the structure of the crystal is the same as at the macro level, right? The large level scale where you can actually visualize it. So let's continue with this video. Let's see what happens when you put this stuff into water. All right. The water molecules surround the individual ions, and those water molecules, here we have them surrounding the chloride ion, they convince the chloride ion, they stabilize the energy around it, and allow it to remove from the crystal. And then water molecules on the other side, oxygen ends of the water molecules here, surround this positively charged sodium ion and remove it from the crystal. And then once the front layer is removed, the lower layers are available, and the process continues until you get the crystal dissolved. Now, when you put milk or salt in water, or milk, sorry, you put sugar or salt in something like milk or water, these chemicals will dissolve. But salt does something a little bit more than just dissolve. So our chemical formula for sugar, C6H12O6, right? Solid. I put it into water, C6H12O6, aqueous. It will dissolve, all right? And it will be soluble in water. We've done that before. But when an ionic compound dissolves, it does something a little bit more. We say it doesn't just dissolve, but it dissociates. It dissociates because these ions are no longer near each other. They separate from each other, and they're surrounded by water molecules. And this is called dissociation. This down here is dissolving, but not dissociating. Right? The water molecules do the same thing. They surround this thing here, and they will allow it to separate from its neighboring sugar molecules, but they don't ionize, form these ions, and dissociate from each other. Okay? So, here's an example of sugar, a little model of sugar, same thing, right? It's getting taken away by the water. When you do put something like salt into water, the result in terms of conductivity is that your water becomes conductive. So here's an example of a solution that has sugar in it, and we're trying to drive electricity through this light bulb. We've disconnected these wires to see if the electricity can travel through that solution of salt or sugar water, but it can't. Here's an example of a salt in solution. This isn't sodium chloride, this is copper sulfate, but electricity can pass through the system because copper sulfate ionizes to form ions. Okay, so ions in solution allows conductivity to flow as well. And we call this a strong electrolyte. Now, have you guys heard of the term electrolytes before? Kind of an old term. It used to be a term that made Gatorade a lot of money, right? Because they came across it when few people knew what it was, and they said, our drink contains electrolytes. People said, wow, that sounds like it's going to give me energy. I'm going to drink some of it, right? What's the code word for electrolytes? Like, what does electrolyte mean? Salt, right? Salt. So, you can make your own Gatorade by taking water and putting salt in it, right? So, I mean, it's not like doesn't mean it's good for you. It serves its purpose. But you shouldn't get too confused about what you're actually buying. It's salt and sugar, whereas regular soda pop is less salt and sugar, right? So that's the difference there between those Gatorade and sugar, right? And soda pop. So the word electrolyte just means salts dissolved in water. A chemical that dissolves in water but doesn't ionize, doesn't dissociate, would be called a non-electrolyte, or one that dissociates only partially would be called a weak electrolyte. So when we say strong, weak, or non, it's how much it dissolves in solution. Not all chemicals dissolve, not all salts, dissolve. So here's another chemical, sodium bromide. Right? Here's another one, silver bromide. When you put these two salts in solution, one will ionize and one will not will be soluble and one will not be soluble. And we have a way to determine which will and which will not be soluble. And it's on the back of our periodic table. So you guys want to pull out your periodic tables? Anybody need a periodic table? Or if you just want another one, it's time to refresh. Accidentally printed out the Oh, I see. Anybody else want one? Did I see you raise hands up? Did you want one? Okay. All right. So on the back of this periodic table, we have our polyatomic ion sheet that we've already talked about. And now we're going to talk about this right corner one, which is the solubility rules. Solubility rules. The solubility rules can predict whether or not a compound, an ionic compound, is going to be soluble in solution. So you put it into water, is it going to ionize, or is it going to just stay together and be a powder at the bottom of the container? Right? So, don't look. All right, here it is, right here. Okay, so here is the solubility rules there for you. And it gives you information about different kinds of ions, right? And the compounds that they form. All right? So, can you with your partner look at these two and see which one is soluble and which one is insoluble? And then we want to know what rules indicate to us that they're soluble or insoluble. Okay, now, remember a long time ago when I introduced to you the polyatomic ion table? That was a pretty good day, huh? Yeah. And remember how I said that at some point we want to become familiar with all these polyatomic ions. And what did I say was going to be our best way to do that? I was just talking about a great business plan about how to make millions of dollars. Remember the day I introduced to you the polyatomic ion chart?
Yes.
Wasn't that a great day?
Yes.
Yeah. We talked about a way that day. We talked about a way that you could gradually remember these polyatomic ions. Do you remember what it was? The way was to use it frequently and for an extended amount of time. The polyatomic ion table here, this chart. Because if you put them into flashcards and yep, I got it, it will last a short amount of time, right? So we want it to be in an extended set of your memory, so we use it frequently, but over an extended amount of time. So when you come across a problem that's associated with polyatomic ions, the goal was make sure this was nearby, right? Where are you supposed to keep it, like in the middle of the night? Yeah, right by your bed. So if you wake up, oh yeah, okay. You can go back to sleep, right? All right? If you do that, if you always have this available and you're working on a problem and you look, okay, I got it now, I got it, right? And you're always using it, then as we get closer to the final, all of the polyatomic ion understanding that you need will be in your brain. Okay? If you don't do that, then you're going to be having to do flashcards before the final, because we're not going to be using this on the final, right? But the same thing goes with our solubility rules. Our solubility rules. Okay? Now, when we come across a solubility question, we want to have this nearby so that you can always flip here, look at the solubility rules, and gradually become familiar with them. If you do that, you'll be significant or sufficiently prepared for the final.
Wait,
Okay?
so why can't we use this on the final?
Because it's expected of general chemistry students that they have these things memorized.
The
Right. Polyatomic ion table and the solubility rules. And every other teacher says, just memorize it and we're done. But my experience is when you do that, they memorize it for a week, but not for 4. And we want to try something different. We want to see if we can gradually become familiar with this stuff over a 3-month period so that in the end, we remember it and it'll actually last for years. I had a student come back after 50 years of teaching and they knew every polyatomic ion still. I was pretty impressed. That's not true. Come on, I'm not 50 years old. Brother. Okay, anyways. The point is, you're going to use this the same way that you use the polyatomic ion table. Okay? If you don't use them, then it's not going to work. It's not going to work. Okay? All right. So which rules apply with this one?
They're solid.
Okay, this one's soluble because rule what?
Bromides.
Bromides are soluble with a lot of stuff. And sodium is an alkali metal. So that's rule 1 and rule 3. Okay, good. So that's the kind of thing we want to be able to do. Rule 1 and rule 3 indicate this is soluble. How about this one? Insoluble based on rule what? 3. Okay, very good. So we have our solubility table that we're going to become familiar with and begin to use whenever there is a question about solubility. Solubility rules. Now, we also need to have the ability to see how a given ionic compound will dissociate when placed into water. What are the resulting ions that are going to come if this dissociates into water? We have a sodium ion and we have a bromide ion. Isn't that interesting? We call this a sodium ion and this one a bromide. Right? Remember we talked about that a while back? Like sodium chloride, this isn't a bromine ion, it's a bromide ion. Anyways, let's do that again with sodium sulfate, Na2SO4. Right? Sodium ions and the sulfate ion. What's the sulfate ion look like? What's its charge? SO4, 2 minus. So how do we know that? That's right. We look at the chart, we figure it out, right? Or it's on the board, right? So, these are the 2 ions we have. How many sodium ions are we going to end up with? 2. We don't do this, right? That doesn't make any sense. We do this, because I'm trying to say that there are 2 of these sodium ions, right? Can you see that in this one compound there's going to be 2 of those sodium ions? All right, so let's see if you guys can then identify how many different kinds of ions, right? The dissociation of these different salts off to the right on that slide there, slide 11, right? Write down the number of those things. You know, the question about why can't we use this chart is a completely valid question, because I think the real reason is because the world of chemistry is driven by a bunch of curmudgeons who just say, this is the way it has to be, this is the way it has to be. Before, it used to be that you had to memorize the whole periodic table, because that was what you did. But that seems, I don't know, to me seems ridiculous.
We
Right?
get a periodic table on the file, but just not this stuff.
Yes, we'll have a periodic table, but we won't have those charts on the back. But the world is changing, and filling your brain cells, I don't know, maybe it doesn't matter. You can fill them with anything you want, but I think it does matter. Okay, did you get them? Let's see. Now, we're trying to learn how to kind of do a bookkeeping thing here. We have to make sure that you had 3 sodium ions and 1 phosphate ion. Who got that right? Raise your hand if you got that right. Excellent, excellent. And this next one, did we get it? Anybody forget the 2 and the 3? Okay. You see why they're there now, though?
Yes,
Okay. Did you get the 3rd one yet, or who needs more time on the 3rd one? Raise your hand. All right. 3rd one is, well, it's not tricky, but generally people miss something in the 3rd one here. Okay, what did we get for the 3rd one? Calcium ion and chloride ions, right? So we have to make sure that we recognize that the calcium ion has a +2 charge. We have to recognize that there's 2 of these Cl- ions. Very good. Who needs time for the last one? All right. Recognizing how salts dissociate into water is important, because if I say I have a solution of a chemical, the chemical is always going to be surrounded by salt or water, by water. It's not just itself anymore. And if it's an ionic compound, you'll have none of it associated together. So in a solution, in a solution of sodium chloride, there is no sodium chloride. None of it is sodium chloride. It's either sodium ions or chloride ions floating around. Okay, so what's the name of this compound, first of all? Calcium permanganate. Very good. All right, anybody want to go over any of these answers here? Okay. So then, which of the following would not be expected to produce chloride ions when dissolved in water?
We have a question actually from the last slide.
Previous one?
For the MnO4,
Mm-hmm.
I get why the O is 1 minus.
This MnO4.
Why is it that?
MnO4?
Yeah, why is it 1 minus?
Oh, how do we know that MnO4 is 1 minus?
Yeah.
That is our periodic table. Sorry, our back of our periodic table, our polyatomic ion chart. Is it on there?
Okay, yeah.
All right, good.
Okay, thank you.
Where's it at? Oh, there it is. It's after the chlorate, chlorine, perchlorate. Okay. So then, look at these compounds. Figure out which one would not be expected to produce a chloride ion. Why might not it produce a chloride ion? Maybe it's not soluble. Maybe it doesn't dissociate, right? Would sodium chloride produce the chloride ion? Yeah, it's an ionic compound, and the solubility rules say that anything from group 1A should dissociate. How about lithium chloride? Yeah? What's the solubility rule associated with lithium chloride? 3 and 1, right? Very good. How about PCl3? What's the name of that compound? Is it phosphorus chloride? What's the name of PCl3? It's phosphorus trichloride. Why is it called that? They're both nonmetals, right? So this is what kind of a compound? Molecular. So molecular compounds are not going to ionize in water. All right? So PCl3, a solution of PCl3, phosphorus tetrachloride, won't produce chloride ions. It might dissolve in water, but there's no dissociation that's going to occur because this is not an ionic compound. All right? Okay, how many ions are going to form upon the dissociation of sodium phosphate? Sodium phosphate. How many ions are we going to get? 3, what? 3, what kinds of ions are they going to be? So we're going to get 3 sodium ions, or 3 what? Phosphate ions, or? So let's draw it out. Do we have to draw it out, or was this one of the ones we just did? Na3PO4. Is this going to dissociate when it's placed into water? What rule says it will or won't? Yeah, first one says that sodium ions, or compounds that contain sodium, are always soluble. So I'm going to get sodium ions and phosphate ions, right? I know the phosphate has a +3 because the polyatomic ion table. If I didn't have my polyatomic ion table and somebody said, hey, here's a compound here. Look at this cool compound I have. What's the charge on this XYZ polyatomic ion? Can you find it on your polyatomic chart, XYZ?
Is this 3 minus or on the polygon? PO4 maybe.
Oh, PO4, oh sorry, 3 minus, yes. 3 minus. How about this one up here? What's the charge on the XYZ here? Is that one on our pure polyatomic ion chart? No. But is there any other way we could know? Yeah, sodium is a +1. So if there's 4 necessary, that must mean that XYZ is what? -4, right? So even if we didn't have our polyatomic ion table or chart with us, we would be able to know that the phosphate has to be a what here? A -3, right?
So you wouldn't put a 3, why would you put a 3 in front of the sodium?
Yeah, we're not done yet. We're not done yet. But you're right. We just identified the kinds, and then we had used the numbers to identify how many. And now, which is this question, how many ions do we get? Well, we get 3 here and 1 there. So the answer is what? 4. 4 ions upon the dissociation of one of these units. Got it? Excellent. So, here's a chemical reaction where silver nitrate combines with potassium chloride. Silver nitrate, is that soluble in aqueous solution?
No.
Tell me which rules tell us that it's not. 3 says that what? Silver is insoluble with chlorides, bromides, and iodides. Is this a chloride, bromide, or iodide? No. So rule 3 doesn't tell us information about this one. What's that? 5. Rule 5 says that all metal hydroxides, that's metals with OH, hydroxide ion. That's not this scenario here. What's that? Row 3 says that if it contains chlorine, bromine, or iodine, so that's not this one here. Row 2 talks about nitrates, NO3. And what does it say?
Soluble.
All compounds that contain nitrates are soluble. So this one is soluble. How about KCl? Soluble or insoluble? Soluble. Which rows? Which rules tell us it's soluble? 1 and 3. 1 and 3. Very good. So we have 2 soluble compounds. We mix them together. See how they've traded places? The metal here goes with the non-metal there. so forth, right? And the result is silver chloride. Is this insoluble or soluble? Insoluble. Rule 3 says that chlorides are insoluble if they're with silver, right? This one's soluble or insoluble? Soluble. Rule 2 says that what? All nitrates are soluble. So here's an example of our chemical reaction, our double replacement reaction, right? AB, CD, AD, CB. Right? Does everybody follow that? Want me to write it up again here again? AB. Oh, that one's horrible. Put it in the recycle bin. They'll recycle it for us. Have you guys heard the bad news about recycling? For about 2 years now, recycling has basically stopped in the